we're recording.
Okay, AP Chemistry, here we go. I'm putting the solution to problem 43 by popular demand up here on the internets for you guys to use to review. Because 43 was one of the tougher ones, the titration problem off the homework. The one we corrected in class today. So just so you have the complete solution, or at least most of the complete solution there, on YouTube for you to watch. So we're going to start here from the setup of the problem. Problem 43 says, aniline is a weak base used extensively in the dye industry. Its conjugate acid, aniline hydrochloride, okay, can be titrated with a strong base such as NaOH. So what we have here, guys, is a titration of a weak base, a weak acid with a strong base. We're saying assume 50 milliliters of 0.1 molar aniline hydrochloride is titrated with 0.185 molar sodium hydroxide. Okay, so let's write down what we know. Throughout this whole thing, aniline hydrochloride looks like this, okay? It's a C6H5NH3Cl. Okay, now you can kind of think this thing here is kind of like ammonium chloride a little bit, with the kind of difference that instead of being just NH4+, okay, we've got this whole shebang here. So really what we're interested in here is this part of it. It's the anilinium ion, C6H5NH3+. This is a weak acid. It's the conjugate acid of the base aniline. Okay, now because this is kind of cumbersome, throughout the problem, I'm just going to call this BH+. The reason we're calling this BH+ instead of the generic acid HA is because this is the conjugate acid of a base that has been formed by gaining an H+ ion. We're going to call this BH+. Okay. So what we're doing throughout the problem, guys, is a titration problem. So we're taking this weak acid, aniline hydrochloride, BH+. We're going to add to this hydroxide ions in the form of sodium hydroxide, and this is going to go back. So we neutralize, go back to the base aniline, okay, plus water. All right, now what we start with. It says we start of the aniline hydrochloride. We have 50 milliliters. Okay, of 0.100 molar solution, and we're going to be titrating this with sodium hydroxide with a concentration of 0.185 molar. All right, so that's the information. So, part A, the question is, what is the pH of the aniline hydrochloride solution before the titration begins? Okay, well in part A, guys, you have to kind of think, if we just have the aniline hydrochloride, we have a solution that contains that weak acid. It is going to be an acidic solution. No titration has happened yet. So this is simply just going to be an ice table type problem. Okay, if we set it up, I'm going to write it down here in green. Okay, so we have BH+. If we have that in aqueous solution, what's going to happen? This acid reacts with water, and it's going to form reversibly hydronium ions. Okay, H3O+. Okay, plus aniline. Okay, the initial concentration here, okay, so let's look here, we'll make our ice table. The initial concentration of this acid right here is 0.100 molar. This doesn't matter, this is going to be 0, and this is going to be 0 also. Because as this reacts with water, this is going to be decreasing in concentration, it's going to be getting consumed. This is going to change, it's going to be minus X, this is going to be X, and this is going to be X right here. And so at equilibrium, what we have is we have the concentration of 0.100 minus X, this is going to be X, and this is going to be X. To solve for the concentration of hydronium, what we're going to do is we're going to set this, make our Ka expression. Okay, so we know Ka for this acid is 2.4 times 10 to the negative fifth power. If we write the expression for that, we get X, right, times X over 0.100 minus X. We can see that X here is going to be negligible for the change in concentration of the acid, so that's going to go away. And so it just becomes X squared over 0.1 equals 2.4 times 10 to the minus fifth power. If we solve for X, we get X is equal to 1.55 molar, and then the pH, by extension, we take the negative log of that, the pH is going to be 2.81. And that is part A. Okay? Before the titration has begun, the pH of the solution is going to be 2.81. Alright, so let's go to part B. Okay, part B is asking what is the pH at the equivalence point of the titration. As you're going to remember, in class we talked about the equivalence point is the point of the titration where an equal number of moles of the base, sodium hydroxide in this case, have been added to the acid. And so this is going to have been completely converted into its conjugate base, in this case aniline. Okay? So what's going to control the pH? This aniline here, okay, we'll write this down here, part B. Okay? Part B. The base that is produced by the neutralization of the acid, this now goes on to react with water. Okay, it's going to accept the proton from water, and it's going to form, again, reversibly, the acid, BH+, plus hydroxide ions. Okay? The solution of this problem is kind of similar to what we did at first. This, again, is going to be an ice table problem. Okay? To find the pH, we're going to solve for the concentration of hydroxide ions, and then get POH, and then find the pH from that. But to do that first, what we have to know is the concentration of the aniline. Now to do that, we need two pieces of information. We have to know the number of moles, okay? Moles of aniline that we have, and we have to know the total liters of solution, the total volume, okay? The moles is easy to find. What we know is that we start with 50 milliliters of the solution, so we have 50 milliliters. I'm going to write that in terms of liters. So 50 milliliters is 0.050 liters of the solution, the original acid solution, okay? I know that the concentration here of the acid, the conjugate acid here, is 0.1 molar. So there's 0.1 moles, okay, of BH plus per liter of the solution. And we see that when this is titrated, there's a 1-to-1 mole ratio. All of this gets converted into B there. So just to multiply here by a ratio. There's 1 mole, okay, of the aniline, which is B, per mole of anilinium ion that was originally present. Okay, so this is going to cancel out, and you're going to see that we've got, to start with, 0.00500 moles of aniline. Okay, that's the number of moles. Now to find the concentration, again, what we have to know is the total volume of the solution. Originally the volume was 50 milliliters. But to find the total volume, we have to know, well, how much of this sodium hydroxide solution was added. So what is the volume of this plus the volume that we originally started with? Okay, to do that, we're going to do some stoichiometry. We know that we started, okay, with 0.00500 moles, okay, of our anilinium ion. Okay, we can multiply here by a mole ratio. We know that to titrate this anilinium ion, if we look at the balanced equation, it takes 1 mole of hydroxide for every mole of the acid. So we multiply by ratio. 1 mole of hydroxide, okay, per mole of BH+. Okay, now to find, so that's going to cancel out. Now to find the volume that we add, we're going to use the concentration of the hydroxide ion. Okay, we see that it's 0.185 molar. We can flip that ratio upside down. In 1 liter of the base, there is 0.185 moles, okay, of hydroxide ion. And so this is going to cancel out the mole of hydroxide. And so what we're going to get, the volume of base that we add is going to be 0.27, let me check. Yeah, 2703 or something like that liters. So if we want to find out the concentration, this is the volume of base that we add. We started with this many, or with 50 milliliters of the solution to start with. So the total volume that we want to divide our moles here by is going to be 0.077 liters. When we do that, we find the initial concentration of the base, which we're going to put here on our ice table, is going to be 0.0649 molar. Okay, so let's plug that in. 0.0649 molar. Okay, this doesn't matter. This we're going to say we have 0, this we have 0. The change again is going to be, this is going to react with water. This goes down in concentration, this goes up by X, and this goes up by X. So at equilibrium we have 0.0649 minus X. Here the concentration is X, and here the concentration